So again, pause the video quickly if you want to jot this example down, and then you can play it when we walk through it. So you have a rock that's being dropped from someone on top of a cliff over some water. We know that it takes about 3.5 seconds for that rock to fall all the way down and hit the water. So the question there becomes, how tall is this cliff? Now that usually throws people off right off the bat because we have one variable, we have time. That is it. So how in the world can you solve this using kinematics if you need three of those kinematic variables? We have to be very careful about what's going on here. So the initial velocity we actually do know. Anytime something is dropped, you have to realize it's dropped from rest. That means its initial velocity that split second when you first let go of it is actually zero. It will not be zero if you throw it downward or you throw it upward, but anytime you drop something, its initial velocity is zero because gravity hasn't really had enough time to grab hold of it. So we say that zero shortly after beginning to increase. The final velocity we do not know. Now, some people want to say, well, when it hits the water or the ground below, maybe the final velocity would be zero. Like if it hits the ground, it stops moving. If it hits the water, maybe it bobs to the top and then it's just floating there and it's zero. Guys, we're talking about free falling objects. The second that hits the water, it's no longer in free fall and we can't apply this. We can't analyze it as such. So the final velocity is actually unknown here. That would be the speed right before it hits the water. It's going to be moving pretty quick at that point. We don't know what that is. Well, the acceleration is actually known. If this is on Earth, we know that all objects accelerate vertically at negative 9.81 meters per second squared. We don't know what the height of the cliff is, but we know that this object fell for 3.5 seconds. All right, so we're being asked how tall is the cliff? How tall is the cliff is basically the vertical displacement. So final velocity is the one variable that I don't care about at the moment. And if I choose the one equation that does not have final velocity, that should be delta y instead of delta x, is VIT plus 1/2. I can write A, I like to write G because it's the acceleration due to gravity. But that's just our kinematic equation, just substituting in delta y instead of delta x and G instead of little a. Okay, but you can see here it's the same thing. Either one of them is acceptable, so it doesn't matter. All right, so if we plug in what we know, our initial velocity is 0. Our time was 3.5. Well, that whole thing is just going to cancel out. Plus 1/2 times negative 9.81. And my time was 3.5 seconds, and I'm going to square that. All right, if I plugged it in my calculator, we get 1/2 of negative 9.81 times 3.5 squared. I get negative 60.09 meters. Now that throws a lot of people off. They say, why is it negative? Well, we have to think about it. We're looking at this rock here, and the rock began up here and ended down here. So which way did this rock move? It moved downward. This represents the displacement of the rock. The rock is now 60.09 meters below where it started. So we just flip that around. If I want to measure the height of the cliff, we don't usually measure with negative numbers. So if the rock fell from the top to the bottom down 60.09 meters, we can kind of flip that around and say that the height of this is just the reverse. So the height of this cliff must be 60.09 meters, since we measure height, in the positive direction from the bottom up. All right, so you're just going to use kinematics, and we're going to adjust that very slightly. So let's look at one more question so you guys have a chance. This one's a little different. Now we're actually going to throw the rock up in the air. So the rock is now actually going to do this. It's going to go straight up and then straight back down. So we're not just dropping it. It's still in free fall, though. Once it leaves my hand, even though it's traveling upwards, goes to the top and comes down, once it leaves my hand, gravity is the only thing acting on it. So let's go ahead and plug in our values. Well, our initial velocity in this case is actually a positive 8. I'm going to assume that upwards is positive and downwards is negative. So we throw this upwards at positive 8. Final velocity we don't know. Again, that would be the velocity right here just before it hits the water. Probably going to be moving very fast, so we don't know what that is. This is still on Earth, so our acceleration is negative 9.81. Height of that is unknown, and the time is 7 seconds. I'm going to wind up using the same exact equation. If final velocity is what I don't care about, then I know that delta y is VIT plus 1/2 g t squared. And then I can plug in everything I know. Delta y is, well, in this case, we have an initial velocity of 8, and that time was 7, plus 1/2. I need to recognize that it's negative 9.81 because gravity never pulls things upwards. And this is going to be, whoops, sorry, that was the last problem. This is 7 seconds. And I have to make sure I square that. If I plug all of that in, I'm going to get, let's see, that's 56 plus 1/2 times negative 9.81 times 7 squared is 49. So this gives me negative 184.35 meters. Again, that is actually the displacement. So that's not the distance. That's not this whole pathway. Okay, that would be the distance. That's actually the displacement from here to here. That is what delta y represents. So I can flip that around again to measure it in the more classical sense. And the height of this cliff must be about 184.35 meters. All right, so just understand you can use kinematic equations much in the same way we have been. You just must be very careful. The acceleration, unless you're on another planet, will be negative 9.81. And just recognize that anytime a rock is dropped, you can assume that you know your initial velocity is 0. All right, good luck with that challenge problem. And yeah, good luck.